Hi, this is problem 7 from the 2016 AIME 1. For integers a and b, consider the complex numbers shown and find the number of ordered pairs of integers a and b such that this complex number is a real number. So in looking at the expression for our complex number, I noticed that there are two ways to eliminate the imaginary component. And one way is probably the simplest, is to just force a plus b to equal 0. And as long as the expression under the square root is positive, that will eliminate the imaginary component. So let's try that method first. So let's look to make a plus b equal to 0. And it looks like, well, we could choose, let's say a plus b is equal to 0. We could certainly choose 0, 0. That works. We could choose 1, minus 1, minus, or plus 2, minus 2, and so on, all the way up to, it looks like the square root, or just below the square root of 2016. If we make this number any larger, then we run into the issue where this starts becoming an imaginary number, and that we'll have to treat as a separate case. And it looks like we can also go up on this scale all the way up to minus 44 plus 44. So this gives us 44 times 2 plus 1, 89. But one of the tricky parts of this is that we have to avoid any condition where a times b is equal to minus 100, because that'll make these denominators 0, and that renders the number infinity, which we don't really consider a real number. So in each of these lists we have minus 10 plus 10 that we have to eliminate. So all totaled, looks like we have 87 of these solutions in our total solution set. So now we have to consider the second case where we essentially have a and b not equal to 0, but we have an imaginary number on the left side that can cancel out the imaginary number on the right side. So essentially we're looking for the case where the expression inside this radical sign is equal to the negative of a plus b absolute value. So essentially we want ab plus 2016 to equal minus a plus b. And if this is true, then the imaginary component over on the left side will be the negative of the imaginary component on the right side, and that will render a real number. So it looks like we have an absolute value sign that we have to break up into two cases. We have the case that a plus b is greater than 0, in which case we can write this expression as ab 2016 is equal to minus a plus b. And this looks like our very usual factorable integer equation. So 1 times 1, add 1 to both sides, factor the left side, minus 2015. Hopefully we remember that that's minus 5 times 13 times 31. And we can write out all the different factor pairs. We have exponent of 1, 1, 1, so we have 8 total factor pairs. If we order them, that reduces to 4 possible factor pairs. So we can write out this as equaling minus 1 times 2015, or minus 5, 403, minus 13, 155, minus 31, 65, and that yields AB minus 2, 2014. This one yields minus 6, 402. This one yields and so on. So it looks like we have 4 solutions, and it looks like we can also interchange a for b given the symmetry here. So what we have here is actually 4 times 2 solutions for 8 in total. Now we have to also consider the case where a plus b is less than 0. And now we can write this absolute value expression as AB plus 2016 is equal to positive A plus B. And we can move everything to one side. To minus 2016. Do the same trick. Factor. And you can pretty much go down this solution and path, and you'll basically find now that you'll pick up an additional 4 times 2, which is equal to 8 solutions. And these solutions are all different than the ones we listed on the right. And looks like we have 8 plus 8 plus 87 for a grand total of 103 solutions. And that's our final answer. Anyway, it's a bit wordy, but hopefully that helped, and we'll see you at the next video. Take care. Bye-bye.